Alright, so sequences, fun stuff. So I want to talk about geometric sequences. So in the last video we talked about an arithmetic sequence. We saw that it was just a bunch of numbers strung together where you were adding the same thing every time. To be a geometric sequence, instead of adding the same thing every time, you're going to be multiplying by the same thing every time. So a good example of this might be this sequence here. As you can see, as you go from one term to the next, all you're doing is multiplying by 2. So you're multiplying by 2 every time here. So this would be one example of the geometric sequence. It could also go the other direction. There's no need for it to always be increasing. You could also be multiplying by a half, or in this case I'm going to try to multiply by negative a half, and notice when I do that my signs alternate. So the number you multiply can be negative, it can be greater than 1 or between 0 and 1. In other words, the sequence can increase or decrease. And there's no reason that it has to be 2 or a half. You could also multiply by 3, like so. Or multiply by anything you wanted to, really. So these are 3 examples of geometric sequences. You may notice if you take these numbers and you start to graph them, so taking this as your y values, for example, and then plotting the number that this represents. So like this is the first number in the sequence, the second number, the third number, the fourth number, the fifth, and the sixth. If you plot these as ordered pairs, where the x value is the number and the y value is the term, you'll notice that the graph looks something like this. So 1, 1, you have a point there at 2, 3, and 3, 9. That's going to be way up there. Your graph starts to look like this. It looks goes off to infinity. It looks like an exponential function. So when we looked at the arithmetic sequences, we saw that they were just lines. So all a geometric sequence is, it's an exponential function. So when we studied exponentials, we saw that we could write them as a times b to the x power, where a was the starting value and b was either the growth factor or the decay factor. So for a sequence, the formula looks very, very similar to this. A sub n is equal to your starting value times that number that you're multiplying by every time, raised to the n minus 1 power. So this here is your explicit formula. So we talked about the explicit formula for an arithmetic sequence was just y equals mx plus b. Well, the explicit formula for a geometric sequence just looks like the exponential function, a times b to the x. We write it using this notation here. A sub n represents the term number, like 1, 3, 9, 27, except it would be the nth number. So if we repeated this n times, a sub n would be that term number that we get. A1 is the first number in your sequence. R, again, is whatever you're multiplying by every time. So here, RR would be 3 in this one, or in this one would be negative a half, or this one here would be 2. And n minus 1 is that power that we're raising this to. It represents the x. So some cool things that you'll notice aside from that formula. So I'll copy this down up here so we can add it to our list of things we talk about. The explicit formula is a sub n equals a1 times r to the n minus 1. Another cool trick that you'll see, let's say that you've got a sequence like this here, and you know it to be geometric, and maybe you know that this term here is 2, and maybe this one here is 32. And you want to figure out some of the other terms. Well, one of the easiest options there is kind of like what we did for arithmetic. We saw that we could find the number in the exact middle of the two that we know using the arithmetic mean. Well, for a geometric, we want to use the geometric mean. So, a little aside here, thinking about your operations. At the very bottom of the operations, you've got adding and subtracting. If you go up a level, multiplication is the same thing as repeated addition, and division is like repeated subtraction. And if you go up another level, you've got where you're raising things to a power versus taking the root of those same things. So when we did the arithmetic mean, you were adding everything together and then dividing by how many things you had. So you were here, and then you went to this step. For the geometric mean, you're going to be multiplying your values together and then taking the nth root. So for example, here, I want to find this term in the middle, so I take the geometric mean of the ones that I know on either side. So 2 times 32. And since I have two numbers, it's going to be the square root, and you don't have to write the 2 there. So here, that's 2 times 32 is 64, and the square root of 64 is 8. So I know that this number in the middle would be 8. Alright, so I use the geometric mean there. I could also then go and find this term here, using the same principle. So this time it's in the middle of 2 and 8. So I know 2 times 8 is 16, and the square root of 16 is 4. So this number here in the middle must be a 4. And I could technically go back and do the geometric mean again and find this one, do the square root of 8 times 32, but I don't really need to do that because now I've got a couple in a row here. What am I multiplying by to get from 2 to 4? Well, I'm multiplying by 2. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 would be 16. Or if I go the other way, what number times 2 gives me 2? Well, 1 times 2 does. So don't feel like you're required to use the formula every single time. You can just think about the patterns there and reason your way through what the numbers might be. Sometimes that'll be the fastest method, rather than trying to reduce down what's the square root of 8 times 32. Well, that might take you some time, whereas you can quickly recognize you're just multiplying by 2 every time. So the geometric mean is another nice trick that you can use as long as it's right in the middle. So we'll add that up here. So geometric mean is useful when you know these two and you want to find the number right in the middle. So you might be asking yourself, well, what do you do if maybe you know this one and you know this one here is 16 and you want to find one of those? Well, there's not a perfect middle between 2 and 16, so you can't really use that trick again, but what you can do is use the explicit formula. So we know that our formula says this: a sub n is a1 times r to the n minus 1 power. We know what a4 is, so we're going to let n be 4. We know what a1 is. We don't know r, that's what we're trying to solve for. And again, we said that n was going to be 4 in this example. So let's substitute in what we know. We know a4 is 16. Our fourth term is 16. a1 would be 2. I don't know r, but I know that 4 minus 1 is 3. So here, solving for r, I'm going to divide both sides of this equation by 2. 16 divided by 2 would be 8. And then the opposite of cubing something is to take the cube root. So here, the cube root of r to the third is just r, and the cube root of 8 is 2. So I can use my formula to discover that r is 2, and then I know 2 times 2 is 4, times 2 is 8, times 2 is 16, and it looks like it works. So that formula that we discovered earlier, that just comes from knowing that it's an exponential equation, knowing this, we can use that formula in a lot of different applications. It's very, very useful. There's one other formula that we should talk about. This one doesn't get used as often. It's the recursive formula for a geometric sequence. And this is really what we're doing when we're saying that I know this term and I want to find the next one. So if you want to know what is a sub n, well, you look at the term right before that, a sub n minus 1, the term that comes right before it, and you multiply that by the common ratio. So this is another formula that's useful. They might give you this formula here. For example, they might say that a sub n is equal to a sub n minus 1 times 4, and the first number is 3. And you want to find the next 3 numbers, for example. Well, you know the first number is 3, so to find a2, well, we're plugging in 2 for n. A2 would just be a1 times 4. So 3 times 4 would be 12. So don't get fooled by the notation. It's not saying anything mystical. It's just saying that take the number before it and multiply by 4. In other words, they're telling you the common ratio there. So if you're going to do the next one, we'll multiply 12 by 4. That would be 48. We'll multiply that by 4 again, and you'd get 192, I think. Hopefully I did my math correctly. So that's a look at geometric sequences. In the next video, we'll start talking about series. I'll talk about arithmetic series first, and then we'll talk about geometric series. So pretty cool stuff here. Really important that you know the formulas and know which one is which. So know that this one here is the explicit for a geometric sequence, and know that this here is the recursive for a geometric series. Alright, there you go.